Hi, everyone. Welcome. My name is Yufeng. You can find me on Twitter at Yufeng, and today we are going to talk about the path from AutoML to a custom model.
My name is Sara Robinson. You can find me on Twitter at srobtweets. And here's what we're going to cover today. We're going to talk about all of the machine learning tools available on Google Cloud Platform. Then we'll start with building a model using AutoML natural language. Then we'll build a similar model using TensorFlow and Cloud AI Platform. And finally, we'll wrap up and share some resources with you. So one of the great things about all of the machine learning products on Google Cloud is that you don't need to be a machine learning expert to get started. So with this pyramid, you can kind of choose your level of abstraction. So the products that we're going to show you towards the bottom are targeted at folks that may have more machine learning expertise. The products, as we move towards the top, are targeted more towards application developers. So at the lowest level, we have these open source, popular machine learning frameworks. So if you're building a model at this level, you're writing all of the code for the model by hand, each of the layers, and you'll need to figure out what infrastructure you want to use to train and serve your model.
Next up on our abstraction pyramid are deep learning VM images. These are prepackaged virtual machine images that have machine learning libraries installed on them already, so you don't have to install them by hand. And additionally, if you want to add things like GPUs to that instance, you don't need to worry about installing the drivers to power those GPUs. Those will also be taken care of for you.
Next up, we have Kubeflow, which is an open source project created by Google that lets you deploy machine learning pipelines on Kubernetes containers. And Kubeflow has this concept of components, so you can break your pipeline up into individual components for pre-processing data, training, and serving.
Then we have Cloud AI Platform's training and prediction services, which abstracts away some of the manual work around scaling up training and prediction and allows you to kind of have a managed service to take care of that for you.
Moving up the stack, we have BigQuery Machine Learning, which lets you take structured data stored in BigQuery and run it through a machine learning model. All you need to do is choose the type of model you want to use, and with a single SQL query, you can have a model trained and ready for prediction.
AutoML allows you to have custom models customized to your data set, and you don't need to do any code for setting up that model, and you can train and serve those models.
Finally, our machine learning APIs let you access pre-trained models with a single REST API request. So you don't need any of your own training data. If you want to accomplish a common machine learning task, these ML APIs are a great way to get started. And since we don't have a ton of time today, we're going to focus just on 3 of these tools. So we're going to start by building a model with AutoML, and then we'll build a model using TensorFlow deployed on AI platform.
So before we dive into each of these components, I just want to make sure that we're all on the same page around kind of what we're calling machine learning and give us a framework to think about how these tools all fit together into this workflow. And so at a high level, we can say machine learning is using data to answer questions. And so when we break that out into kind of a structure, we can think of the data as training inputs, and that goes through our machine learning model, and we can answer our questions or get labels or predictions or classes from the model. And so you can swap out these things for real examples.
So you could have almost any type of input to a machine learning model. One example is a picture. So the input to our model here is the pixels in this image of our cat, and our model outputs the label cat. We could also have text as input to our model. So we could take the headline of this article about a Raspberry Pi and build a model to categorize the article. So in this example, it'll categorize it as a technology article.
So we were thinking about situations where we could use a machine learning model to predict some sort of a useful label on text. And so being developers, we naturally, this led us to thinking about Stack Overflow. We've got some text, and we need to tag them with something. Right? There's lots of great tags on Stack Overflow for all sorts of questions. And in particular, in the machine learning space, we have lots of different machine learning libraries. And we thought, in a hypothetical world, wouldn't it be neat if while we're typing a question into Stack Overflow, it told us some recommended tags, right? Tags that make sense based on the question that we're asking.
So first, to do this, we'll need lots of training data. Luckily, there's a data set available as part of the BigQuery Public Datasets program that has lots and lots of Stack Overflow questions. To be exact, it has 26 gigabytes of Stack Overflow questions over 17 million rows. So we're going to use this table to get some training data for our model.
And with that data, we're going to use that as our training data and push that through AutoML. And AutoML will give us the ability to train up a model without needing to worry about the model architecture, and we can really just focus on getting the data into the right form, making sure it is exactly what we want and none of the things we don't. And then at the end, we'll have a REST API that we can call and get predictions from. So let's dive in and take a look at what that looks like. So in our example, that question that we saw earlier, we would go into AutoML, and for our first pass, let's just try to categorize questions as either TensorFlow or not. And so in this example, of course, it would be TensorFlow. And to get this data together, Sara mentioned we have the BigQuery public data sets. And thanks to BigQuery's very robust SQL engine, we can do a couple of pre-processing steps right out of the gate. And there's a couple of really useful functions on BigQuery. We really got a chance to dive into some of the functionality there that kind of extends beyond just the standard SQL body of functionality and operate on these big data sets. So one of the things we first noticed when we looked at the questions is that in this public data set, there's HTML tags just everywhere. There's pre-tags, code tags, paragraph tags, bolding, italicized. We don't want any of that, right? None of that is useful for identifying whether someone is asking about a TensorFlow question or a different machine learning library. So we're going to strip all those out. The tags also happen to be separated with vertical bars. Not great if I want to make my data look anything like a CSV. So replacing those with commas. And in this example, we're going to pull out just kind of related machine learning libraries. We're not going to try to tackle the bigger problem of tagging questions, even web development questions as TensorFlow or not, and just stick within kind of this subdomain.
So hold on a second. Couldn't you just write an if statement? I feel like most TensorFlow questions have TensorFlow in them at some point. So you could do something like, if TensorFlow, then the tag equals TensorFlow. Maybe you don't even need machine learning for this.
This is true. People do love writing TensorFlow when they're asking about TensorFlow questions. And this applies to a lot of questions on Stack Overflow, right? Like if you're asking a question about pandas, you're probably saying, in pandas, how do I do X? And then maybe you paste in some code. And in that code, you write import pandas as PD. Oh, there's pandas again. And so Stack Overflow is kind of an interesting space where the tags oftentimes line up directly with the questions being asked. However, that's not always the case. A lot of times for questions, people will just dive right in. They'll just come out and they'll just say stuff, and they might not even bring up what library they're using. They just want to know this specific detail, and they perhaps rely on the tag to indicate what library they're talking about or what context they're using. And so we want to train a model that can be robust to these model names, because if we just have a model that just looks for TensorFlow somewhere in the question and it says, aha, there's TensorFlow, that's not a really good model, right? That's not really machine learning. That's an if statement. And so what we can do is take our data set and we're going to replace all instances of the word TensorFlow and Matplotlib and pandas and scikit-learn and PD and PLT and TF and Keras. We're going to replace that all with the same word. And what better word to replace our machine learning libraries with than avocado? It'll prevent our model from cheating, and we'll have lots of avocados everywhere. And everything is better with more avocados. Your toast, your data sets, just everywhere. So lots of avocados. And so here's an example of some of these pieces of data. We've already stripped out those HTML tags and some of those new lines. So everything is kind of compressed down now, right? And because a lot of times Stack Overflow questions will be really long. You got to scroll and scroll and scroll. We want to make it so we can see more than one question in a window. And you can see some of these questions that are tagged with a couple of different libraries. And you can learn about the avocado data set and import avocado from avocado and avocado.layers and look at avocado predictive models. It's avocados everywhere. So let's see what happens now as we pull this data into AutoML, and we'll switch over to the demo and look at kind of what it looks like really on AutoML. Great. So we have here, this is the view of when I've pulled the data into AutoML. We can see kind of some examples of the various texts that we have, lots of avocados everywhere. And we have our two tags, other and avocado. There's just as much avocado in the other tag as there is in the TensorFlow tag. So the model won't be able to distinguish between questions that have lots of TensorFlow in them and the questions that don't. And so once we've trained up a model, it'll take us to the evaluation folder. Training takes longer than the time we have here, unsurprisingly, given the size of our data set and kind of the complexity we're hoping to achieve here. So AutoML natural language uses a number of different natural language processing approaches to try to find the best model that we can get. And so here, I would say we did pretty well here, right? Like, all I had to do was hit train, and then we just went off, we worked on our slides, we did other things, and at some point I got an email that said, oh, your model's done training. And so I was like, oh, great. Now I can just come back and see how it did. I mean, it really saved us a lot of effort. There's no debugging of code. There's there's debugging of the SQL code before, but once we start training, it got a lot easier. And so we can even check out the confusion matrix, right? Because we only have those two classes, we can kind of show that. And what's neat about this confusion matrix is instead of just having a kind of bland confusion matrix for us to look at, we can actually click into these. And we're getting all this for free. I didn't have to write any code to go and identify things like false negatives and questions that should have been predicted other, in this case, but were labeled as TensorFlow, or questions that were predicted as other, but it should have, or the other way around, right? It should have predicted TensorFlow. So we can see some of these questions that are not accurate, right? And then kind of zero in on why that might be. We can adjust our data, we can adjust our approach, we can adjust how we go about this process. And so it's really kind of a useful thing there. So let's go up, and we can click predict here, and what we'll do is grab an actual Stack Overflow question, right? So let's say here's one. It's about simplifying URLs for .NET, and it's clearly not TensorFlow, if I do say so myself. And what we can do is we can paste that text into the predict box. So sometimes when you finish training a model, it's like, oh, here's a REST endpoint. Good luck with that. Go and figure out authentication on your own, write up some code, run it, then you can call it. But it's really nice that we have this text box here that we can actually just click predict and see what we get back. And so you can test all sorts of text into the body here. And so that's our has TensorFlow model. So let's switch back to the slides and look at how we can improve on this, right? Because knowing whether or not a model is TensorFlow or not is not that earth-shattering, if I do say so myself. You can do better than that, right? We can tag it across all those tags that we saw. Keras, matplotlib, pandas, scikit-learn. We should be able to get a question and not just say, oh, this is not TensorFlow, but that this is pandas. And we can use that same data set we did before, but kind of process it a little bit differently. Instead of saying TensorFlow or other, we'll actually write out the specific library that it is using. And our data set across these 5 kind of tags, there's a good number to work with for each one, which is nice. And so let's see what that looks like. We'll switch back over to the demo station, and here we'll jump straight to the evaluate screen. And we can see our 5 tags. Overall, the precision and accuracy were good. We can click into one of these, let's say pandas. And we can look at the specifics around each of these tags. And again, see the true positives, examples of false negatives, examples of false positives across each of these tags. So you can click into these and actually see specific examples, the full example, not just the excerpt, and the predictions in detail, as well as going back. And you can notice there's a delete button. So in some cases, you might have data that you're generating yourself, and you might find like, oh, that's just an erroneous piece of data. I just need to get rid of it. It's actually not supposed to be in my data set, right? We're pulling data from Stack Overflow, but your data might come from user data. People might have typed in garbage. It might be malformed in some way. So again, we'll go and find another Stack Overflow question. Here's a question about Keras. And we can copy that question into the predict tag. And we can test out how it does, right? So we're hoping that Keras will be one of the top tags that come back. So we see that it comes back with a great amount of probability. It also thinks that pandas might be related, and that very marginally TensorFlow also might be related. Another example is with kind of a question that touches across a couple of different things. We got pandas, we got data frames, and we got Keras. And so we can paste that in and run predict on it, and we get very strong signals around Keras, and there's a little bit of TensorFlow on the side too, because Keras is, after all, now largely folded into TensorFlow. And so one of the things that might be worth pointing out here is that you'll notice the numbers don't add up to 1, right? Because we're predicting across 5 different classes. The breakdown isn't a strict probability distribution because it can have multiple tags that come back, not just the one true tag, so to speak. So let's switch back to the slides, and we'll click through the screenshots in the event of live demo failure. And now we'll move on from kind of the AutoML use cases to a more custom machine learning workflow. And why might we want to do that? Why would we move on from something that works really well, right? We're seeing really good results. It seems that we can just click train and then we can just get a sandwich and not have to do anything else. But perhaps we want to solve a more custom problem. Or maybe we have different inputs, not just text, but text plus images, all in the same model. Or maybe we just want to learn more about custom natural language modeling and add that to our machine learning tool belt. So we'll kind of try to go through this process in a way that isn't just, draw a circle and then boom, there's an owl. We'll try to get the steps in between as well so that we can kind of show that roadmap more clearly. So I'll toss it over to Sara, and who will kind of go through this process.
Thanks, Yufeng. So before we dive into some code, let's talk about what we mean by custom model. So when we say custom model here, we're going to be writing code. In this example, we'll be using TensorFlow and Keras. We'll write code to pre-process our data, define our model architecture, define each of the layers of our model. We'll run training and evaluation. We will deploy our model, and then we will get predictions from our trained model. So machine learning models can a lot of times seem like a black box and a lot of magic. It's actually not magic. Under the hood, it's just a bunch of matrix multiplication. So if any of you remember y equals mx plus b from your algebra classes, this may look familiar. So when you train a machine learning model, you have inputs, which are your features, and then you have your prediction, the thing you're trying to label. And then you also have these weight and bias matrices. And the idea is that as you continue training, you find the optimal values for these weight and bias matrices to get accurate predictions. So obviously, when you start training, these matrices will be randomized. Your predictions won't be very good. As you continue training, they will get better.
Hey, Sara. This all seems really reasonable with kind of numeric data here. We even took the time to make sure these matrix multiplies were correct. How does this then apply to other data formats like we have here with our text data?
That's a good question. It may not be super obvious of how to convert any type of data to a matrix, but you can actually represent pretty much any type of data in matrix format. So in this image example, we have this color image of a cat, and really all an image is just a bunch of pixels. So this particular image, every pixel has a red, green, and blue, an RGB value. So this image becomes 3 matrices of RGB values. Let's say you have categorical data. So let's say there's a column in our data set, and it has 3 possible values, the strings sitting, stretching, or running, to describe different actions. So the way you represent categories for a machine learning model is you do what's called one-hot encoding. So you create arrays where the number of elements equals the number of possible categories for that particular feature. And then all of the indices are 0 except for 1, which corresponds with that particular feature. Now you may be thinking, wouldn't it be way easier if we just encoded these numerically as 1, 2, 3? That would be easier, but then our model would interpret these as continuous numerical values. So it would interpret stretching as greater than sitting, running is greater than stretching, which isn't necessarily true. So we'd want our model to treat all of these different categories equally. And then finally, for free-form text, which is the type of data that we're dealing with, there's lots of different ways you can encode free-form text as matrices. We're going to be talking about one specifically called bag of words. This is my favorite one to get started with if you're new to natural language processing. So what this method does is it treats, you can think of it as a bag of Scrabble tiles, where instead of a letter on each tile, you have a word on each tile. So all of the inputs to your model, all of our Stack Overflow questions, are individual bags of words. So it won't be able to detect the order of words in a sentence, but it will be able to detect the presence or absence of certain words. And Yufeng's going to tell us a little bit about how bag of words works.
So I guess in our case, though, instead of a bag of words, we might have some avocados mixed into that bag.
Exactly.
Bag of avocados. So in this kind of simplified example, just to talk us through the concepts, let's pretend that we do not know English. Our entire vocabulary, we're learning English, and the only words we know in the entire world are those 10 listed there under vocabulary. Data frame, layers, series, graph. It's a very technical approach to learning a language, I suppose, to learn these words first, but be that as it may. Then we have these labels, right? We'll simplify down, condense it for this purpose to just 3 labels: Keras, pandas, and matplotlib. So we're going to try to use bag of words to categorize sentences as one of those labels. But we only know those 10 words, right? So if we go to the next slide, we can see an example sentence, how to plot data frame bar graph. Not the best English, perhaps, but when we look at it, we only recognize 3 words, plot, data frame, and bar graph. The rest of it is all gibberish, right? So pretend you don't know what the words how, to, and bar mean at all. That's just nonsense words. And so when you look at that, what you can do is you can then encode from your very limited vocabulary of 10 words, that sentence. We can encode that sentence based on the position within our vocabulary. So our vocabulary is going to be ordered. And so we see, in this sentence, there's the word data frame. It happens to be the 4th word, but we're going to say that it's going to turn on the first bit in our array, because data frame is the first word in our vocabulary. It's the first word we learned ever, let's say. And the 4th word in our vocabulary is graph. It's the last word in the sentence, but we're going to turn on the 4th bit in that array to a 1. And so this is kind of why it's called a bag of words, because we don't care about the order of the words in the inputs. It's like we took the sentence, broke it up into words, and just tossed them into a bag, pulling out one word at a time and only recognizing the ones we knew. So we pull out a word and it says data frame. We'll turn on the first bit. Pull out a word that says bar. I don't know what that is. Throw it out. Then we pull out another word that says plot. I know what that word is. That's the 6th word. Turn on that bit. And so when you finish grabbing all the words out of the bag, you have an array that has encoded the sentence based on your understanding, your representation of the world. And you do that for every sentence in your data set. And so now each example has been encoded into this array that has ones for all the words that showed up in each of those respective sentences. And so this is kind of a graphical representation of that, right? Each word kind of goes to the different spots in our vocabulary and yields the 1s and 0s. And you can do the same thing for the prediction. It's a little more straightforward. There's only 3 words. And so whichever ones are the correct labels for a given sentence will turn on with 1s and leave the other values as 0s. And so this brings us back to our matrices.
Yes, so now we know how to encode our text as bag of words. So this is what the inputs will look like to our model. For this simple example, we just have a vocabulary of 10. As you'll see in a moment, we'll use a larger vocabulary for our Stack Overflow data set.
It's a little bit larger.
A little bit bigger.
Yeah.
And then our prediction is just an array with the size of the number of labels that we're using. So how are we going to build our custom model? We're going to be using a variety of different tools to pre-process our data. We'll use BigQuery to get the data, as Yufeng already showed us. We're going to use the exact same data set to train our custom model as he used for the AutoML version. We'll use pandas, which is a really handy Python library for examining our data set, doing some feature transformations. We'll use a utility function from scikit-learn to encode our labels as multi-hot arrays. And then finally, we'll use Keras to convert our text to bag-of-word matrices. We're going to use TensorFlow to build our model, specifically the tf.keras API. We will run training and evaluation in Colab. Colab is a cloud-hosted browser-based Python notebook. And since our model trains pretty fast, we can run it right in Colab. Then we will deploy it on Cloud AI platform and generate some predictions. So what will the code look like to encode our text as bag of words? Luckily, we don't have to do the process of getting the top words from our vocabulary and converting them to matrices by hand. Keras has a utility function to help us with this. It's called a tokenizer. So we instantiate our tokenizer by telling it how many words we want it to collect. So it'll take the top 400 words from our vocabulary in this example. Now, this is a hyperparameter. You should try with different values depending on the size of your data set and the total number of unique words in your text corpus. So then we train the tokenizer on our text data by calling fit_on_text, passing in our train question strings, and then we convert our text questions to bag of words matrices using the text to matrix function. And then we will build our model architecture. So we're going to do this using the Keras sequential model API. This is my favorite API for building models. Essentially, it lets you define your models as a stack of layers. So it'll be really easy in code to visualize what our model looks like. This is going to be a deep neural network, which means that it will have some hidden layers in between our input and our output layer. So our first layer is going to take an input of our vocab size, which is 400. So we're going to take our 400 element bag of words array, and then it's going to convert that into a layer of 50 neurons. And the way it's going to do that computation is through an activation function, which is called ReLU. The great part about Keras is we don't have to worry how that's implemented under the hood. We just need to know the right activation function to use. We're going to have one more hidden layer. So our model is going to take that 50 neuron layer and transform it into a 25 neuron layer. Again, the size of your layers is another hyperparameter that you can use to experiment with different values. So the outputs of these hidden layers aren't going to really be meaningful to us. Our model is just using them to represent complex relationships in our data. But what we do care about is our output layer. So our output layer is going to be 5 neurons because there's 5 possible tags in our data set. And we're going to use the sigmoid activation function.
So Sara, let's talk a little bit more about why we're using sigmoid here. A lot of times we see different activation functions in neural networks, and oftentimes, in particular, softmax is a common other alternative activation function that's chosen.
That's a good question. So remember for this model, it's a multi-label, multi-class model. So that means that our model could predict multiple tags for a given question. So what sigmoid will do is it'll take each of those 5 elements in our output array, which correspond with the labels, and it'll return a value from 0 to 1, indicating the probability that that question corresponds with that label. And the values will not add up to 1, since there could be more than one label per question. You said you've seen softmax a lot, which is a good point. If you instead had a model where you could only have exactly one possible label per input, you would use softmax as your activation function. And what that would do is it would still return that 5-element array, but all of the inputs would add up to 1. So here's an example of our machine learning model's output using sigmoid. And we can see that in this example, there's a high probability that this particular question corresponds with the first and last label in our data set. Finally, we'll compile our model so that we can run training and evaluation. We pass it the loss function we want to use. This is how our model calculates the error between what it predicted and what it should have predicted. And this is the thing that our model is trying to minimize. The optimizer we choose tells our model how it will optimize those weight and bias matrices after each iteration. So running training and evaluation in Keras is pretty straightforward. We call model.fit. We pass it our train questions encoded as bag of words, our train labels. We're going to run training for 3 epochs. This means that our model will iterate over our entire data set 3 times. The batch size is 64, which means that our model will examine 64 elements from our data set at once before it updates the weights. And then to evaluate our model on our test data, on data that it's never seen before, we just call model.evaluate. We pass it our test questions, our test tags, and the batch size. Finally, we're going to deploy our model on AI platform with this new alpha feature called custom code. Custom code lets you run custom server-side Python code as part of your prediction request. So this lets you configure how you pass your inputs to your model, how you format them, and also the format of the prediction output. So we're going to make use of this feature so that our client can be super simple. All we want our client to do is just pass the text to our model, and then on the server, we'll use that tokenizer we created to convert it to a bag of words before we generate the prediction. If you want to try custom code, stay tuned for an announcement soon. If you want to try it really soon, you should fill out this form to request alpha access. And I will have a link to this on the last slide, so don't worry if you don't get it now. Finally, we will be making predictions. And we'll do this using G-Cloud, the Google Cloud CLI. We can just call predict on our model, pass it some examples in a text file, and we'll get our predictions. So let's see it in action. If we could go to the demo. So here I have my Colab notebook, and I've already run the first couple cells. So I'll just briefly explain what happened there. So here we are importing all of our libraries that we're going to use for this. We're then authenticating this Colab instance so that it knows about our cloud account. We're downloading that same data set that Yufeng used for the AutoML models. And then we are converting our data set to a pandas data frame. So this is a really nice way to visualize what our data set looks like. So our data set in this form is a comma-delimited string of all of our labels. We want to convert this to a multi-hot array. So we need to split that string up. So what I've done here in this next step is we've converted each tag row to an array of all of the tags. And then we're going to use multi-label binarizer, which is part of the scikit-learn library. So we've then converted this array of string labels to this one-hot encoded array. And this is our lookup array of all of the possible labels in our data set. Then we will choose our train size. In this example, we will use 80% of our data for testing, or for training, and then we'll reserve the other 20% for testing. So we've got a lot of questions here. And then we will split up our encoded labels into the train and test sets. And then finally, this is where things get interesting. I've written this class to tokenize all of my text inputs. So we create that Keras tokenizer, we train it on our training questions, and then we return that tokenizer, the text to matrix call. So we return that bag of words matrix. And this cell is actually where I call that class to create the bag of words matrices. So just to show you what this ends up looking like before we feed it into our model, we have, this is just the first example in the training set. We have a 400 element array because we had a 400 word vocabulary size with a bunch of ones and zeros indicating the words from our vocabulary that are in this particular question. So now comes the fun part of building and training our model. So what I just ran in this cell is we're going to use this Python tool called Pickle to save the state of our tokenizer. Because we'll need to use our tokenizer when we make predictions. Here we're creating our model, and this looks exactly the same as the code that I showed you on the slide. And then in this step is where we actually train and evaluate our model. So you'll notice here that I use validation split. What this does is it takes a subset of my training data and it uses that to validate the model, to make sure that it's actually learning and it's not overfitting to my training data. So what I want to see here is that the training loss is decreasing, but that the validation loss is also decreasing. If the training loss was decreasing and validation loss was increasing, it might be a sign that my model is overfitting. So now it is time to test out our model locally. Haven't deployed it to the cloud yet. So I have this class for pre-processing the text, so taking the text string, converting it to bag of words, and then loading the model and generating a prediction on it. So here we have 2 test strings, which are from real Stack Overflow questions, and we will call our custom model prediction class and generate a prediction. So we can see that our model predicted Keras for the first one with 91% probability, and then pandas for the second one, it looks like with 89%. So our model is working. It's still just local to this Colab instance. So the next step is to deploy it to Cloud AI platform. So what we're going to do here is we will package up those scripts that I just created. I saved them to my local Colab instance. And then we're going to copy our saved model and our tokenizer to a cloud storage bucket. So I'll run this command. And then the next command will package up all of my code and set my current project to the one where I'm hosting this demo. And now we're going to run the deploy command. I'm going to change the name of the model to Next 2019. And we'll run that deploy command. And if we go over here to our model, let me zoom in, and refresh, we should see that new version deploying. So while that deploys, let's go back to the slides. And I'm going to talk about one more thing. So it's really important to remember that behind these machines are humans. It may sound really obvious, but as people that are involved in any part of the model building or deploying process, we are responsible for the predictions that are generated by our machine learning models. So this means it's really important to take steps to make sure that your training data is representative of the people that are going to be using your product. So one example is, let's say we train a model to identify 10 different types of cat breeds, and we train it on thousands of images. Accuracy is really good, 99%. We deploy it, and someone comes along and uploads a dog picture. Now, our model's entire worldview is just those 10 cat breeds. So it's going to probably try to classify the dog photo into one of those cat breeds, maybe even with high confidence. So it's really important to make sure that your training data is representative of the people using your product, and also that your model is using the right features to make those predictions. The good news is, there's lots of great open frameworks to help with this. I'm going to use one in particular called SHAP. It's an open source framework. You can find it on GitHub. And what SHAP does is it lets us interpret the output of any machine learning model. And it can tell us which features are most impactful in making our model's predictions. The way that we use SHAP, first we import it, and then we create what's called an explainer object. There's a bunch of different types of explainers as provided by SHAP. we're going to use the deep explainer since we have a deep model. And we pass our deep explainer our model and then a subset of our training data. And then we can call SHAP values on our explainer object to get the attribution values. And what these attribution values are is going to be an array of the length of the number of features we have with attribution values on how each feature impacted our prediction. So high positive values would indicate that that particular feature pushed our model's prediction up, and low negative values indicate that it pushed our prediction down.
So Sarah, this really sounds straightforward for like your standard structured data set. You got a CSV file, you got columns with all sorts of different attributes. But we've got text data here. It's just free-form all over the place, avocados everywhere. How can we capture feature importance in a text model?
That's a good question. So since we're using a bag of words model, and we've got a 400-word vocabulary, essentially what SHAP will do is it'll treat each of those 400 words as different features. So we can look at the attribution value for each word to determine which words signaled our model's predictions.
So it's like having a really wide table, 400 columns.
Exactly,
Gotcha.
400 column table.
Great.
So what I've done is create a visualization to highlight the top 5 signaling words in blue and the lowest signaling words in red. So what we have here is a question that is about matplotlib, and our model is picking up on these specific words to make the prediction. So it's picking up on the words color, PLT, fig, ax, and then words like data or the number 4 are contributing least to our model's predictions. So this is good because it shows us that our model is working relatively well. If instead it was picking up on words like for or in or the to make predictions, we may want to go back and revisit our training data. Here's an example for TensorFlow, and I actually used SHAP to help improve this demo. So the first time that we ran it, I sent Yufeng a screenshot. I was like, hey, look, it's using the word TensorFlow to predict that this is TensorFlow. Maybe we should take that out of the question.
Perhaps, yeah.
So that's how we decided to use the avocado replacement, to make sure that our model was working really well. So for the TensorFlow example, it's picking up on words like variable, session, graph. This is a pandas example. It picks up on column, data frame, and the negative signal words are for and each. And so let's see this SHAP in action. So if we could go back to the demo, it looks like our next 2019 model finished deploying. So
Hooray.
yes, so we can go generate some predictions. So we're going to write these predictions to a text file, and I'm going to change the version that I'm getting predictions from, and I'm using gcloud here to get predictions on my trained model. And we can see that it works. We get 2 arrays of 5 elements, and we will visualize those predictions a little bit nicer here. So we can see that for the first one, it predicted chaos. The second one, it predicted pandas. So now comes interpreting our model with SHAP. So to do that, we will first pip install SHAP and this library called colored, which I use to color the output text in blue and red. So since those are not included in Colab, we will install them. And once they're done installing, we will create our SHAP explainer, just like the code that I showed on the slide. And our Keras tokenizer is actually a dictionary corresponding with word frequencies. We are going to turn this into a list so that we can use it to look up the corresponding words with each feature attribution number. So one handy function that SHAP has is this summary plot function. And what this tells us is the words that have the highest magnitude in our model's prediction. So it's not necessarily the highest positive value. It could be high negative values as well. So we can see, for example, the effect that each word has on a particular prediction. So data frame is impacting pandas predictions most, which makes sense. It's probably a negative signal word for TensorFlow and matplotlib. And then for plot, we can see that's signaling matplotlib most, and perhaps a negative signal word for pandas. So you can see a couple examples of the top signal words there. And I've written this function to color our text, the top 5 highest and lowest signaling words. So we'll just print a couple of examples here. So this is a pandas example. We can see it uses the words column, not a number. Generic words like use or does don't signal the predictions too much. For TensorFlow, we get sesh, ops, tensor, and these words that are related, some of them to other labels in our data set are pushing the prediction down. So those are negative signal words. And then I'll just scroll through some other examples here. We have another Keras example, words like LSTM, layer, dense, which are pretty common words you may recognize if you've ever built a model in Keras. And then we have a couple more examples here. And then one last one on matplotlib. So that's a simple example of how you can use SHAP. And if we could go back to the slides.
So during this session today, we've kind of gone from getting our data set together, loading it up with avocados, and then pumping it through AutoML. We did one with TensorFlow or not, and we did a model which categorized TensorFlow, matplotlib, pandas across a couple of different libraries. And so that perhaps is like a more robust version of that approach. And then we went and kind of built up a similar model from scratch using a bag of words or bag of avocados approach. And then we ran that in CodeLab, deployed that model to Cloud AI platform, and used the prediction service to actually make calls and get predictions back. And then we fed that into SHAP to interpret our model to figure out what words in each example contributed most and contributed least to identifying the labels that it created.
So just to wrap up, these are resources to all of the different products and open source projects that we covered. One thing to note, we are working on model interpretability support for AI platform. So if you have a use case for that, we'd really love to hear what you think. And to stay in the loop on updates on that feature, please fill out this form at the bit.ly link, bit.ly/model-interpret-interest. And if you want to try out the custom code feature that I demoed when I deployed my model, you can fill out this form to request access to the alpha, bit.ly/cmle-custom-code-signup. And finally, we would really love your feedback on this session. So please remember to go into the app and add your feedback on the feedback form.
Thanks, everybody, for coming. It's been great.
Thanks.
Fun.